So the topics I'm going to be covering today, I mean, some of you will already be fairly familiar with them, but I'm hoping that some of you won't be as well. We're going to be talking about threshold signature schemes, and in particular, going to be looking at two big ones, one for BLS and the other for Snore, and talking about just how they work and what techniques they use. So to those of you who don't know what a threshold signature is and what it's supposed to do is distribute trust. So typically, if you want to have a signature, you have a public key, you also know your own secret key, you're able to use your secret key to sign anything that you want to, but you are the only person that can do that. If we're now instead in a setting where there is some kind of shared secret key, a classic one in the cryptocurrency space would be if you maybe don't want to be keeping hold of your own secret key, but you don't want to trust a single other person to do that for you, you might distribute the key over lots of different people and then just say that I'm not going to trust any one of you individually, but provided a threshold, enough of a majority of people are there and present and generate the signature, then I'm okay with that being a valid signature. So what this then means, if you have t+1 out of n, is that if you have a single or maybe one or two authorities that are corrupted, they can't do any damage. A majority can, but a small number can't. And if you have it so that maybe someone goes offline, maybe their hardware gets deleted, maybe they just, asleep at the time, you can still generate a signature without their help. So this is important for liveness. So the two algorithms we're going to look at for threshold signatures, one of them is backwards compatible with BLS. This I would say is the easier one. And the second one is backwards compatible with Snore, and this is the Frost signature scheme. There's a third backwards compatible signature, which some people are interested in, which is ECDSA. These are much more challenging, so I wasn't planning to try and cover those in half an hour. But in all the schemes that I'm talking about, both the schemes, what we're going to want is we're going to want that the threshold signature, once generated, looks identical to a normal signature. We don't want some kind of special purpose scheme which can be thresholdized. Instead, we're looking for something which already works with the infrastructure which is out there. So almost every threshold scheme I have ever seen, with a couple of exceptions, but very few, uses Shamir's secret sharing scheme in some sense or another. The reason being that it's just really good. It's the main technique that we know in order to get these P out of N things to work. If you happen to not follow my explanation, maybe because it's not a very good explanation, or maybe because I just don't spend enough time on it, then Wikipedia does a pretty good job, so you can look at that in your own time. So basically how Shamir's secret sharing scheme works. We have a secret we want to share. For this context, I'm referring to the secret as a secret key, because if we're talking threshold signatures, the secret is a secret key. In other contexts, it might just be referring to it as a secret. We want to distribute the shares of this secret over n different players, and we want t of them to be able to reconstruct. So what we're going to do is we're going to generate a polynomial of degree t, whose 0th coefficient is our secret key. This polynomial is going to be completely random. You just sample t different secrets from the field, and then you use those in order to construct that polynomial. So now we have it that we can evaluate this polynomial, and we can evaluate it at n different points in order to get n unique shares. In practice, by the way, the points which you'd evaluate it at, they wouldn't be 1, 2, 3, 4, all the way to n. They would be roots of unity in order to make things fast. But for the purposes here, I'm saying 1, 2, 3, 4, all the way to n. In order to reconstruct, we're going to need to use something called Lagrange polynomials. So a Lagrange polynomial is going to be something which is going to be equal to 0 at I, ik, ij I've said here, oh sorry, 0 at all of the i's apart from the very specific index which we happen to be interested at the time, in which case it will be equal to 1. And if you have roots of unity, these can be generated very, very quickly using fast Fourier transforms. Here we don't have roots of unity because we're doing it the easy way. So the easy way to then generate such a polynomial is to just say, well, it needs to equal 0 at all points apart from ik. So I'm going to just take x minus I1 times x minus I2, etc. But it needs to equal 1 at ij. So what I'm going to do is then I'm going to just divide out what that polynomial equals at ij in order to get it equal to 1 at that point. Now that we have these Lagrange polynomials, we can reconstruct, because we have that our polynomial, our original polynomial f of x. If we take the secret, if we take our secrets and multiply each of them by the corresponding Lagrange polynomial, we're going to have that this is going to reform our original polynomial, basically, because if you have p points, then f of x, well, we know that's going to evaluate to the correct thing at those t points because that's how it's defined. And likewise, for if we sum up sk times the Lagrange polynomial, well, that's just going to disappear unless we happen to be equal to the point of interest, in which case it's exactly going to be equal to skj. So this just means that our secret, the thing we want to reconstruct, is going to be the sum of our Lagrange polynomials evaluated at 0 multiplied by the corresponding secret. So I hope you followed some of that, or else that you're already familiar with it. To apply this to a BLS signature scheme, we're going to want to essentially do Shamir's secret sharing, but in the exponent. So the BLS signature scheme is really popular because it's aggregatable, basically. And what this means is that if you have n signatures which are generated on the fly, then you can compress those all down into one signature, so you don't have to store all of them and you can just verify one at a time. In a threshold scheme, it also thresholds up really nicely because we only need one round of interaction. So we don't have to do something which you'll see that we have to do in Snore, where we sort of send a message, get a response, and send another message. Instead, we can just send one signature, and then someone can run a combine algorithm in order to get the full signature back. So how does it work? First, we have a public key, which is going to be equal to G1 to the power of our secret key. In order to sign, we just hash the message into the group, and then we take the exponent of that message to the power of sk, and that is our signature. In order to verify, we need to compute the same hash on the same message, and then we just check one pairing, namely we pair our public key with our hashed component and check that it is equal to E of G1 paired with our signature. And what this basically guarantees is it guarantees that that signature has been generated correctly. So we're still relying on Fiat-Shamir here in a way, because we're hashing into the group. Well, Fiat-Shamir is the wrong word, but either way, the random oracle model. The reason it's one round is because the only thing we're hashing here is public information which you know at the start of the signing process. So when you start signing and when you start verifying, you know you don't have to generate anything else in order to use that hash. So when we're doing our threshold signing, we're again going to have our polynomial, which is of degree t. We're going to have our secret shares, which are going to be the evaluations of that polynomial. We're also going to have some corresponding public keys, which are basically going to be what the BLS public key would be if that secret share was in itself a public key. And the reason I've described it like this is because signing in the threshold sense actually works exactly the same as signing in the normal sense. You just use your secret key share rather than the secret key. In order to then generate the signature, you have all of these key of these signatures, which have been generated using the normal sign algorithm. In order to reconstruct, well, we're going to need to know our Lagrange polynomials for the T people that are taking part right now. So not all, so assuming we don't have all N people taking part, we just have some set of T people taking part. We compute those Lagrange polynomials, and then we have that our signature is going to be equal to the combination of those signatures taken to the power of the Lagrange polynomials computed at 0. To see that this works, we first have our signature. This is just equal to the product of our signatures to the power of Lj of 0. That's how we've defined the combine algorithm. If we then look at what our signatures themselves equal, we have that sigma j is equal to z to the power of sk ij. Got some weird indexing due to the fact that we have any different set of T people taking part. We don't necessarily know which T are taking part. But either way, the thing that's happening here is we're just substituting in what we know the signature is equal to. Now we have a group operation happening in the group. We switch over to what's happening in the exponent. So when we multiply all of our group elements, instead we now add all of the field elements that in the exponent. So that product becomes a sum. Then we see that it is going to, that the summation that we have in the exponent is exactly equal to f of 0 due to how we have defined the Lagrange polynomials. This is where Shamir's secret sharing is actually happening. That's exactly the algorithm from Shamir's secret sharing. And then finally, we see that the f of 0 is exactly equal to our secret, and therefore the signature looks exactly like the signature which would have been generated if there was just a single party that knew their secret key. Okay, so I'm now sort of about to move on and sort of describe how the same scheme works pretty much, well, not the same scheme, but the same ideas work in the Snore threshold signing scheme. Rather than having to write out my Lagrange polynomials every single time, I'm just going to tell you that this is what they're equal to, and suggest that you try and remember that, because I'm not going to remind you again. I ran out of room on my slides. So the Snore signature scheme is very popular because it doesn't require pairings. All you need is a group in which you believe the discrete logarithm holds. There were patent issues when it was first introduced, all the way through to 2008, I believe, according to Wikipedia, which meant that many applications have had to rely on an alternative, ECDSA, instead. And ECDSA was basically designed in order to not look like Schnorr, such that the patent wouldn't apply, such that people could sign in a discrete logarithm group without having to pay for a patent. But since that patent is now expired, people are slowly moving back to Snore because in most respects it is better. I mean, it's certainly simpler, it's certainly easier to thresholdize for that matter. Bitcoin in particular is set to switch to Snore signatures from November, I believe. So now they've been thinking, if we move to Snore signatures, then we can actually use threshold signatures, and Frost has been looking at ways to do that. The Snore signature scheme, in case any of you aren't familiar with it, we have that the public key is just equal to d1 to the power of the secret key, same as for BLS. In order to sign, sample a random field element, compute r equals d1 to the power of r, hash that group element together with the message, and then you compute z equals r plus c times your secret. Your signature is then your group element, capital R, and your field element z. So that's quickly as I could. In order to verify, we compute the hash of m and the group element r, same as in the signing algorithm, so should get the same value c. And then we check that r times public key to the power of c is equal to g to the power of z. The big thing to notice here, the big reason why it is different from BLS and why it is a little bit harder in order to make these schemes a bit more threshold, is because that first element R is included in our hash. And R has some secret information which the verifier is not allowed to know, generated on the fly. And so we're essentially going to need to have 2 rounds in order to first generate the nonce, then get our challenge C, and then generate the second element Z. The first thing I'm going to describe is how not to do it. So the simple way in which you would think to do it is, okay, first we need to generate our nonces. So we're going to do that exactly as you would for a normal sign. We now know which T people are taking part. If any of them go offline, we're into some trouble, but we're going to assume they don't go offline. We've got T people taking part. Okay, let's generate our group element, our nonce, as just being the product of all of those RIJs. In order to sign for the second round, we now have our combined nonce, our threshold nonce. So we're going to hash that in order to get C. And then in order to compute our second message, we're going to say Zj is equal to Rij plus C times Skij Lij of 0. So basically our Shamir secret sharing component is in that Skij times Lij of 0. And we're going to return that. In order to get the second component of the message, you just sum of all of these values up. That should be equal to the sum of the RIJs plus C times the secret SK, and that should verify. There we go, signature scheme. This is very broken. It's in particular broken under concurrency. So if you have multiple people who are signing at the same time, then an adversary could take advantage of that in order to forge a signature. So the scheme I suggested here is a moderate simplification of a scheme which was described in an old paper, GJKR. So don't use the scheme in that paper. There was a security proof. However, there was also a paper that came out a couple of years ago, which basically pointed out that a lot of the security proofs in multi-signature schemes don't work. And the reason why they don't work is because the reduction is essentially reducing things down to the one more discrete log problem. So in the one more discrete log problem, you have Q challenge components, Q plus 1 challenge components, I'll say, because it's easier. and you are allowed to query for up to Q of those discrete logs, but not for the last discrete log, not for the Q+1 discrete log. And if you're then able to produce all Q+1 discrete logarithms, you're able to break the assumption. The problem that these schemes ran into is they didn't accurately count the number of queries that the reduction made to the one more discrete logarithm oracle over the 2 different iterations of the adversary, or multiple different iterations if you get into the forking lemma. And what actually happened is their reduction made too many queries. So it looked like it went through, but when you actually counted up the number of queries made, it didn't. And that paper introduced a sub-exponential attack, but actually there is a polynomial attack on these schemes, which was in a, I believe, crypto paper this year on the insecurity of ROS. And I have actually looked at this paper, I've implemented it, I've had a look at it. It runs in a few seconds on my laptop and my implementation is not very good. So please don't use this scheme. What Frost does instead, and this is a trick which has been copied in a couple of papers, I should say a lot of papers came up with it sort of at the same time, is they decide to use 2 nonces. So rather than having your Rij, we now have both Rij and Sij. When we're combining, we're not just going to combine up using a product. Instead, we're going to generate a hash. And this hash is going to take as input the message plus the index of the people signing plus all of the nonces. And then we're going to use that in order to randomize our combined nonce. I should mention this is the case in Frost, which is not the case in Music 2. The way I've described this scheme, it is very important to hash, firstly, the message, but also the indexes of the parties taking part. If you don't do that, it doesn't work. I don't have time to explain why. But then in the second round, we can sign as before, as in the naive scheme, but this time because we have that extra randomizer, that extra A, we then have to add that on in order to get Zj, and then we can combine Zj as you would expect. Now, the reason why this second nonce works, well, certainly when it comes to the reason why it works from the security reduction, which is sort of the easier bit to explain, is because it basically means that you have to make the adversary still makes the same number of queries to its reduction in order to learn what the signatures that it's querying on are equal to. But the reduction makes less queries but the reduction now has 2n challenges from its one more discrete log problem rather than n challenges. So then when you sum up the number of challenges that it makes over the 2 iterations, when that happens to equal n+1, you now actually have 2n components in your challenge, so that number of things that you have summed remains firmly below your upper bound. And this is why the reduction then goes through. Okay, so I'm going to wrap up a little bit early, so leave lots of time for questions if there are any. One thing that I will conclude by remarking is that both of the schemes that are mentioned here have a secret key, which is a field element as opposed to a group element, which is not very efficient to encrypt using Algomal. And so one of the papers that I have worked on sort of fairly recently is then saying, okay, if you do have want to be able to share your secret key using AlgaMal? Is there a way to do this? And the answer is basically yes, but it's going to cost you one extra group element and I think 2 extra pairings per signature. Okay, thank you very much.
Thank you so much, Mary. I'm going to ask the audience if there's any questions. You can also enter them in the chat if you don't want to talk or unmute yourself, if anyone has anything that was unclear. Well, Sylvain says thanks.
Yes, I have a question.
Go for it.
Seems, Mary, you favor Snore over BLS despite the increased communication complexity. Is it something wrong with the assumptions, the bilinear assumptions, or is it just purely efficiency, compute efficiency?
I mean, there's certainly nothing wrong with the assumptions as far as I'm aware. I actually quite like both approaches. I don't necessarily think one is better than the other. I think that they are good for different purposes though. So one thing that you do have in the Schnorr setting is that you have your nonces being something which you have to like publish in advance of when you're signing and have those there for possibly a very, very long period of time. And these need to be accessible to all of the different people who are signing. So you just end up with higher communication costs, at least in the threshold setting. Whereas BLS, you don't have that. It's one round, you combine all your signatures, there's your signature, here you go. The downside is that for BLS signatures, you need to have that your system that you're working with supports pairings. And where this is true for Ethereum, it is not true for Bitcoin. Also, if you are working in pairing groups, there is slightly higher overheads because in order for the pairing-based groups to be secure, you need to have your base field have 381 bits, I believe, rather than 256 bits. So this just adds a little bit of cost.
Thank you.
Awesome question. Anybody else?
Yeah,
Patrick, I see your camera's on. Go ahead, Sylvain.
Yeah, I just asked in the chat. I'm just curious, are they like software implementations you would recommend to look at more like for learning purposes? Like now you just like presented the various steps of the mathematics and let's say some simple implementations, because I assume maybe the sort of like real world production implementations are maybe complicated a bit because of all kinds of details that need to go in. Yeah.
So it might be worth looking at, I think that it's called PiEcc on GitHub.
Okay.
This is a Python implementation of elliptic curves with pairings attached.
Yeah,
and you should find that that implementation is a lot easier to work with than something which has been heavily optimized.
Yeah. Okay. Okay. Thanks.
All right. Anybody else? Last call. All right. I guess not. Well, thank you again, Mary. That was an awesome introduction to signatures and how to use them. I think we have actually a 15-minute break between now and the next talk, so everyone can just hang out, have a break, or yeah.
It was broken. Oh, I don't have to record this if you want to.
It'll be helpful for people who are missing it.
Why music was broken, the original one?
Yeah, because there's two musics, isn't it?
It's exactly the same reason, actually. So I was talking in a very sort of threshold concept because that's what I was talking about. But the security reduction, which I think when they were writing, they were probably, copying old crypto papers and using the same techniques. It just doesn't accurately count the number of one more discrete logarithm challenges over the 2 iterations. And I mean, I think this is because the reduction forks. So actually keeping an eye on the number of challenges which have been made is pretty, you have to be on it.
Okay, but it was broken for the same reason then as the...
Yes.
And then just for the other question, just I remember you mentioned that the broken threshold scheme is obviously broken, but like what's the attack there? Is it that you can negate someone's public key and kick them out of the set, or is it you can just forge their signatures?
You can forge signatures.
Okay, this is like really bad. That's
Yeah. So one thing that you do need in order to forge the signatures is you need for there to be I think 256 on open queries at the same time. But assuming you have 256 open queries, which often you do in these systems, because where you want to have something that is like simulating a one-round scheme, you would just have all of your nonces open, ready to sign whenever someone comes along eager to sign. Those would all count as open sessions.
okay. So like an open, so just to clarify, so an open session is when I've pre-computed the R value and I've given it out.
You've given it out, but you haven't yet signed.
No. Then what do you think about the ECDSA ones? I know they're not part of the talk, but people are implementing them now for Ethereum. I think Fireblocks does.
Yeah, it's basically the operation is a little bit trickier, I think, because they have to do an inverse inside an MPC, which is like not a polynomial operation. So you can't just use group homomorphisms and all the rest of it. So in order to get that to work, you actually genuinely need like a proper MPC protocol. And, you know, MPC is a hard problem. There's a lot of cryptographers working on it. Not an impossible problem, but certainly a lot trickier than just a BLS. Here's how you combine things.
I was going to say, I mean, it just sounds like people should be using BLS. I don't get why they're working with Snore for multi-sig. It seems like the easiest solution. Like it seems like the easiest protocol.
You need to have pairings implemented. And you know, if you're not thinking about threshold schemes at all, then Schnorr would make sense in a lot of ways because it's very simple, it's very efficient, it's sort of very well implemented. You have smaller sized groups. Like there's a lot of reasons why you would use Schnorr, and often in these threshold settings, you are trying to make your signature look like it was generated by just one person. So for that type of situation, yes, it would need to have an alternative for Schnorr.
And then I guess one last question is, you know, for ETH2, is move BLS or will ECDSA still be an option there?
Sorry, you've crackled a bit there.
Oh, sorry. So for ETH2, ETH2 that will eventually be released in a couple of years. That's really a joke. It's are people moving the BLS then as a default, or will it still be ECDSA?
I think BLS is the default.
Okay, BLS will be the default then. That's all my questions.
I'm glad you asked. It really hyped up this talk even more.
So why not using Schnorr? What was the kind of trade-offs? What are the trade-offs between using BLS versus Schnorr? Like I know on your slides you mentioned that Schnorr obviously does not depend on pairings, but so what are the, I don't know, maybe a few reasons why one would, like in ETH2 they use BLS, so why not Schnorr and vice versa?
So I think the big one is that if you don't need pairings, then your group has 256 bits. If you need pairings, then your group has 381 bits. And the speed at which you can sign is a lot faster if you're talking 256 and 381. I mean, these are all within the realms of doable. We're talking small differences. But significant enough differences that if you can work in a group that doesn't have pairings, and sometimes it's better.
Okay, nice.
You know, the program you implemented for the attack, was it difficult to implement?
No. It's just a small little script that uses PiEcc, by the way. PiEcc.
And also I have a question, a basic question for the solution that you mentioned. If the indices are not in the hash, this will be broken and this will be forged. Can you explain a little more about?
Okay. So I think as I described it there, I had taken a small improvement to Frost, which is sort of I'm aware of which works, which is I only computed one A for all of the participants rather than a different A for each participant. So I think if you're computing a different A for each participant, it might be different. But if you're just computing that one A, then if you have it so that you don't include the indices, then you're going to end up with two different possible hash values, C, the actual C, which is used in the Snore signature, depending on who signs. So if you're a malicious person and you say, okay, I'm malicious, so I'm going to use this nonce here, and I'm going to use this same exact nonce in this other setting and convince an honest user to try and generate a signature with me, then in the first setting, you get a different C for the exact same aggregated nonce R. And this allows the ROS attack, which I was mentioning at the start of the talk, to go through, because what that does rely on is exactly this, on being able to generate two different possible hashes for the same nonce, and that only then decide which hash function you genuinely want to use and then make that query. Sorry, I realize that might not have been the easiest to follow.
Yeah, I see. Yeah, thanks. Is it also necessary to check that each signature is, if we call it them as some basic signatures that are not finalized, is it necessary to check the validity of them, or it is assumed that the signers are honest in general?
So I think checking the validity of them is more something that you would do if you combined your signature and then it didn't verify, because then you'd be there saying, why doesn't it verify? This should verify, and that would allow you to find the faulty party very quickly. So I'd say those are more there for the sake of liveness than they are for security. If you're able to generate any signature which verifies with a correct set of honest parties, then it should be okay.
Yeah, thanks.
Now, this is give me another question, actually. So I know the ECDSA papers, there was one where you could detect on a board, as in you can detect a faulty party who has not cooperated with the signature. Can you do that with the BLS or the Snore schemes?
Yep, provided you have that public key share. You just check the check the signature essentially against what it should be with the public key share, and if that doesn't verify, then you can say, oh, the only way this cannot verify is if there's been faulty behavior.
Okay, cool. Because I know one of I think the original ECDSA threshold scheme couldn't detect the boards.
But no,
I think because
that sounds kind of bad.
Yeah, because GoFeather had two papers for the ECDSA. One was detecting the board, and the other one wasn't. And that was like the second contributions to do that. Okay, so that's not an issue then. It's more BLS.
No, I mean, in order to like actually check for aborts, you then have to like implement the algorithm to check for aborts, but that's not a big deal. Like it's fine. I think people usually don't expect a lot of aborts usually.
Yeah, I mean, I would only implement it for debugging.
Sorry?
I would only implement it for debugging.
What, seriously?
Probably. I guess no one talks about the aborts, like how to detect them.
I guess they probably would be talking about them if they were actually causing a problem. So maybe it's not a big deal. Well, it would become a big deal if we didn't have a way, I suspect.
But then in ETH2, do you need to like for the validators, are they using BLS like threshold signatures at all, or just normal signature like
Multi-signatures, I believe.
multi-signatures? As in like everyone just signs it there. That's just
Yeah.
okay.
Yeah, no, I think that because you have really nice algorithms for aggregating sort of BLS signatures as you go, and because the cost of verifying a multi-signature is just multiplying together all of the public keys, it's actually not that big a deal to use multi-signatures in that context rather than threshold signatures. The big downside of using multi-signatures rather than threshold in lots of situations is that you then have to compute the public key from scratch every single time. But in this case, computing the public key is quite quick.
Is that because it was done in the exponent, or?
It's not even in the exponent. It's just a I should say addition. It's just an elliptic curve addition. I say multiplication.
Okay.
I work in multiplicative notation, but.
Okay, so in threshold is addition, in multisig is multiplication. I'm just trying to work out the difference. So in the multisig approach, you're multiplying the public keys, and in the threshold one, you're adding them. No, okay.
In the threshold one, the public key is fixed. There is only one public key. Whereas in the multi-signature one, what you do is you take it as input everyone's public keys, and then you use those in order, like per signature, in order to decide on what your current public key is. But this isn't relevant for threshold schemes because there is only one public key in those settings.
Okay.
Since we have 1 more minute, I missed some part of your last slide that you describe your recent work. And if I remember correctly, it is a distributed key generation system.
Yes.
And yeah, what is the relation between the threshold signatures and also the result of that work? And also you mentioned that the secret is the group element, while in the Snore signature and also the BLS, they both, we have the field element. And is it possible to extend your recent work to some field elements or something like that? Yeah, thanks.
No, it's not possible to extend the recent work to field elements as far as I am aware. This is actually I would say the biggest problem with that particular work, and this is the reason why we went to some effort in order to have wanted a unique signature scheme, because we wanted it to be applicable to random beacons. This is the reason why we decided to include one of those in the paper. It was genuinely because we can't cover BLS and can't cover LGML.
Thanks.
I think you should do like 2 of these at each event, these tutorials. It's really cool. Like last year you did one and I actually follow your recommendations. I got the book. I have yet to get deeper in. But you know, maybe a very quick question. It's like there's this, I don't know if you know Jaslyn. She works with Andrew right now, and it was at Cornell. And she saw me, I was outside nearby here. I'm in Ithaca reading this in the sun. And she told me, oh, you're reading this, but this is outdated. And she has yet to explain me why. I don't know why, actually.
Oh, what would you say is the up-to-date book?
I don't know. That's the thing I need to know. But I mean, I think maybe pairing based crypto is, I don't know what's the deal. I don't know. But anyways.